record. Okay, so it's going to be more of a chill lecture today. Probably going to be able to let you out a little bit early. So this is sort of like our mid-year break. Before we start getting into some of the heavier type of theory, we're just going to talk about testing, which is like not sort of a functional consideration, except for property testing. If you know what property tests are? Okay, so we're going to talk about property tests, which is a type of testing that was pioneered by Haskell. So, like the reason we're sort of doing this type of, talking about these menial considerations is because you need to hear about Quickcheck, because it's a technology that was sort of born out of the functional paradigm, and it's pretty cool. What else do I have to say? Good job submitting A1. We'll mark it. We're just marking the induction question. That's taking a really long time, so hopefully soon we'll have it evaluated for you. A2 was released on Friday, so take a look at it. I think it's at least 4 weeks you have it to, yeah. So remember that I pushed the deadline back by 1 week. Is there any concerns before we move forward? We'll talk a little bit about so I'm going to talk about signaling in kinds, then we're going to talk about property testing, and then we're going to talk about the exam a little bit, just some of the policies and some stuff that happened last year that I don't want to happen again. It was nothing bad. Well, it's a little bit bad, but we'll talk about it in due time. Okay, so signaling in kinds. So we're always trying to write total functions in Haskell. And it's not always possible. We've talked about this a little bit. Like just having division in the system means we're not going to have all functions be total. But that being said, we can introduce provisions to make all of our functions total. So let's first just consider a couple of ways that we can sort of bottom out or diverge. It's not possible for us to ensure ahead of time that our functions terminate. Like, for example, this is a trivial function foo. Give it the empty list, it returns false. If it finds 0 on that list, it will return true. Otherwise, it's just going to return foo of the tail, right? So this is going to search a list for a 0. What will the answer be if I search this for 0? Can't? -10? There's no 0 from -10 onward? Am I checking that it ends in 0? Oh, okay. I think, yeah, I'm checking if did I write this right? Maybe this should be an X's here. Let's pretend this is, okay, I'll just rewrite the function. What I want to do is just write a function that searches a tape for a 0, an infinite tape. Okay, so let's write that. You guys got to help me today. My daughter's getting her molars, and that's been quite difficult for us. Okay, so foo of an empty list, there's no 0 on that. Foo of 0 and anything, there is a 0 on that. Foo of something else, and that's non-zero, should just be foo of x's. Okay, so this should be doing 0 tests. What? That's not the right pattern match. So, oh no, that's the mistake I made before. I want to do that. Okay. Okay, so is there a 10? Is there a 0 on this? Yes. Okay, but what happens if I make this a plus? No. Okay. Is there any way for us to tell ahead of time that this function is going to diverge in this way? Why not? Well, why can't I generally tell if a function is going to terminate given on input? That's the halting problem, right? Like we can't solve that. No one can solve that. It's provably unsolvable. Okay, so the point I'm trying to make here is there's no way around being able to tell if our Haskell functions are going to terminate or not. Okay, so let's just give up. Okay, there's no point trying to address this problem. If our functions enter infinite loops, they enter infinite loops. Okay, that's not even a bad thing. You're going to be working with streams on A2. And they're supposed to run forever when they're supposed to run forever. Like, is there anything technically wrong with this searching? No. Like, what if the next one is the 0? We don't know. Haskell's not aware of that it's sort of incrementing in this way because it can't reason. Yeah, I was trying to use ChatGPT to help me generate some exam questions for terrible. Terrible. I think I broke it, actually. I asked it for a question. Because there's a lot of questions which are just like evaluate this Haskell expression. And I said, let's try this out. I said, Here's one of my questions. Try to generate another version of this. I said, here's no problem. I said, that's not a legal Haskell expression. I said, oh, whoopsie, here's another one. I said, that's also not a legal Haskell expression. The next time you suggest a problem, can you ensure that it actually is legal Haskell expression? The thing starts spinning. I wake up to this morning, it's still spinning, right? So it can't do Haskell yet. Can't do math. It's pretty funny. In my 1001 class, we had a student said, I gave this expression to ChatGPT and it evaluated to this, but when I gave it to Python, it evaluated to this. So which one should I trust? And I want to frame this and put this in on my wall, but ChatGPT is not source of truth, guys. Right? The programming language is the source of truth. Okay, so let's focus on decidable problems instead of the ones that we can't decide. So these are problems that will terminate on every input. We can make that as an assumption. So let's ensure then instead that our functions never terminate because they like throw exceptions or something like that. So we need some way in Haskell. And like, as I said, we're always going to have functions which are going to be non-total like division. So we need to introduce some things into the system for what we call signaling adversity, right? That is saying something is wrong with the current setup without erroring out. So we've discussed maybe and nothing, and we're going to stick with number one mostly for the rest of the term. I think having one extra piece of data to indicate error or nothing or something went wrong is mostly adequate is adequate to take any function and make it a total function. You just find the subset of the domain which would error out and just designate that to nothing. But the problem with using maybe is that you have to use this just decorator, and decorating and undecorating stuff gets kind of messy. But we're going to learn that functors and applicatives and monads are going to make that all go away. We're going to introduce the either data type. So this is going to give us a little bit more leverage. This is going to be like a union type, right? So I'm going to be able to say we have a type that is either integer or string. And we're going to have to decorate that as well, because we're going to have the left hand side of that union operator and the right hand side of that union operator. But typically what this is used in the context of signaling is that the correct answer is going to be loaded into right, and left is going to encode a bunch of errors, right? So this is why it's called right. Right is a synonym for correct. So when we're using either for error handling, we pack the errors left and the correct answer is right, because right is synonymous with correct. After that, I want to show you how to make smart constructors. We're just going to work through a little class example because we may want to create data, but then reject data that's ill-formed at the time that we're trying to construct it. This is sort of like shoehorning in object-oriented programming now into our system. And then finally, we're going to talk about kinds, because maybe you never considered this, but what is the type of maybe? Huh? Well, yeah, it doesn't. So maybe has to take a type before it becomes a type. We have maybe ints, we have maybe strings, but what's maybe itself? So it's called the kind. So we have higher kinded types, and that's going to be the thing that we'll discuss in the last part of this lecture. Okay, so let's recall again the definition of the data constructor maybe. So you give me a type, abstract type A, and I build you a new type. And this new type has nothing and all of the things in A with the just decorator over them, right? So if these were integers, you'd have just 0, just -1, just 1, all of the integers, and then nothing. And this is the standard way of signaling that a computation has failed. So let's rewrite the tail function as a non-total function as a total function. So why is tail non-total? What thing from its domain doesn't have a value? Empty list. What's the tail of an empty list? Well, it doesn't have a tail, so that's going to be a problem. So tails take lists to lists, but the tail of the empty list throws an exception. And this is bad. Like we can't pattern match against this. This is just an error. This isn't data. This is Haskell dumping out. So what we want to do now is intervene in such a way where we can actually say, oh, whoopsie, this function doesn't actually have a return value, so let's do something else. So we're going to say we can have a safe tail type of function, which takes lists of A's to maybe a list of A. And I would like that's sort of why we called it maybe, right? Your functions can perhaps fail, right? So you're maybe getting an answer back. So here's how we can implement that safe tail with a maybe. So safe tail of empty goes to nothing. Right, so this now is going to replace error, right? Instead of getting an error handed back, you're going to get nothing handed back. And you can pattern match against nothing. We can test for nothing. I think the nullary function tests for nothing. And then otherwise, if you're not trying to find the tail of the empty list, you're trying to find the tail of a non-empty list. Recall here at line 3 that there is no baggage, right, with respect to having an empty list because that pattern was covered at line 2. And then the problem is that you have to have this jest decorator, right? So now if you want to keep processing these lists, you're going to have to take the jests off, if you wanted to concatenate these lists and then put the jest back, right? So you can have safe tail 1, 2, 3 to get just 2, 3 and safe tail empty to get empty. But if you've then wanted to take this list and append it to another list, you'd have to take the jest off of this, sort of then append them and then put the jest back. But again, we're going to learn how to avoid putting things in and out of containers quite soon. Okay, so let's design so that we've done this. You've been doing this in your exercism. We're going to be doing this a lot. So I think next week or maybe the week after, I want to think about a problem of summing together a list of like maybe integers. And we're going to have to figure out how to sort of recurse in such a way where there may be a signal, an error sent up that recursion chain. So like we'll put a pin in that, but that's going to require some, well, new pieces of technology. What I want to do now is just sort of develop a fake sort of object constructor. So let's create a new data type for student data, right? So a student at least has a name and an ID. Let's say a student name is a string, and let's say student ID is integer. I'll just change that to an integer. And remember, these are these new sort of new type operators that we introduced last week. We can use these. You can totally replace this type with data if you want. Doesn't really make a difference. It's just for readability. Okay, so let's say we have a type. What did I say? Name was a string. We have a type ID. That's going to be an integer. And I want a new type for students, or new data for student, where a student is a student decorator. These don't always have to, so we're obligated to have a constructor here, but this constructor doesn't have to be the same name as the data. It just typically is. It doesn't have to be, but usually we do that for reasons. Okay, so a student, I want to parameterize this with a name and an ID. Okay, so let's see if this is working. Perfect. All right, so I can already have students. Drake, what's Drake's last name? Does he have a last name? Is bad is his last name. Okay, 1, 2, 3, 4. Oops, we need to drive show. Is Drake his real name? It can't be his real name. Okay, so there's our student. Drake is bad. 1, 2, 3, 4. Okay, but suppose I want to reject things like, there's numbers in here. Maybe there's like characters. Drake's doing the Drakey things he's doing. And like maybe maybe I want numbers to be like 8-digit long. Okay, maybe let's say we want student IDs to be 3 digits long. We want to enforce these two things. So at the moment, nothing is stopping us from creating ill-formed student data. So what we want to do is create something called a smart constructor. And it's usually something like make a student by giving me a name and giving me an ID, and then I'll return to you then I'll maybe return to you a student, right? Because now we're going to want to reject ill-formed student types. Okay, so let's focus on a few things. The first thing I want to be able to do is validate the name. Okay, so we'll just start putting in a framework here. I'll say make students. Okay, that's undefined for the moment. So we need maybe 2 functions here. One to validate the name and another one to validate the ID. So what does a validate name look like? Well, I want to take a name and I need to go to a bool, right? This maybe is undefined for the time being. We don't want to do too much. Undefined. And to validate ID, we take an integer. Oh, sorry. We take an ID and we map that to a bool as well. So validate ID is undefined. Okay, which one do you want to work on first? ID or validate name? You want to work on ID? Okay, so suppose we want to make ID verify that the number that it's been given is a 3-digit number. How can I do that? Pardon me? Pardon me? Yeah, use the log, use math. Okay, but this is not as easy as it seems in our paradigm. Why? Yeah, like how do I convert an integer to a float? Does anyone know how to convert an integer? Has anyone done any casting in this? Pardon me? Yeah, okay. So you're gonna have to use this on your assessment. So this is kind of important, right? Because we changed the polynomial data type a little bit to have natural coefficients. So you're gonna have to multiply a natural coefficient by you're gonna have to multiply a natural degree by a integer coefficient. So you're going to have to do a mixed type of computation, and I'm going to show you how to do that now. Okay, so let's look at the stuff that's in the system. Do we have a log? Cool. We have log base. How does log base work? So log base, I give it maybe a base and like 100. This should be 2 if the input's correct. Great. But notice that like 123 has 3 digits, but we don't want to utilize this. So then how can I get rid of the decimals there? Do we have a floor function? Perfect. Okay, so I can floor this log base 10 of 123. Oops. Pardon me?
Yeah, except one problem takes, as you can see there, a real float, doesn't it?
Let's see here what's happening. Floor takes a real fraction and returns something that's an integral. Yeah, and I think floats are part. Okay, so hold on. What did we have before? Okay, so we should be able to floor log base. I did this yesterday. Okay, hold on. Let's just do this. Floor of 1.2. Sure, floor of 1.2, the float. Okay, so if I take, we have to be careful here. So I want to take log base 2 of 100 and 110 maybe. That gives us that. Wait, that's not possible. Why does that say 6? Oh, why am I doing 2? Thank you. Okay. So why can't I floor this? Oh no, I can't floor that. Okay. I don't know. Jeez. Thank you. Okay. Okay. So this is working, but the problem is if I cast this as an integer, it won't work. Okay. So I have to do something with that integer. So there's something called from integral or from integer, I believe. Whoops. Okay. And this takes anything that's an integer and makes it a number again. And things that are numbers can then be made into floats, right? So there's sort of like a type hierarchy at play here, right? So I can't go from integer to float, but I can go to integer to number and then number back down to float. So I can do something like this. Okay, so if foo takes x and we'll say this is an integer. And this returns, okay, so I need to say log base of 10 of from integer x. And then I should be able to do stuff like this. And now I should be able to put floor here. So I can say foo of 100 is 2. Foo of 1,000 is what? Am I? What on earth is happening? Did I break Haskell? Log base B10 of 1,000. I hate floats. God damn it. Is there a rounding function? Let's try rounding this instead. See why we don't use floats, kids? This is okay. Let's use round instead of floor. Jesus, I didn't know that. Um, okay, so that's fine. So we have our ID here, which is going to be an integer. So we just have to round and hope we're rounding in the correct way. This isn't sort of mission critical code, so who cares? Okay, we'll just get the vibe of this. We want to round log base 10 of from integer ID, right? So the relevant thing here is know that from integer exists. It is a thing that can help you do these conversions. You don't have to convert into a float afterwards, right? Once something's a number, then you can do sort of mixed arithmetic against it. Was it not working? Oh, that's right. And I need to ask if this is equal to, what was it? 2? Well, I'm either off by one. Let's see. Whoops. Okay, let's see. Validate ID 100. True. Okay, so I need to say this is no. Yeah, I want to check for 3-digit numbers. Okay, so this is fine. So we've checked 3-digit numbers work, 4-digit numbers don't work, 2-digit numbers don't work, 0 doesn't work. Okay, so we have a validate ID. So already here I can say, okay, make student is, let's check. Let's validate the ID of the ID. And if it's not the case that we have a valid ID, then what? Then we have, I suppose we just say nothing. Okay, and we also want to say if it's not the case that we have validate name, then we get nothing as well. But let's just see how much is working already. Oops. You guys have to help me today. I'm really tired. Yeah, maybe this. Yeah. Oh, look, there's no, Jesus, there's no inputs. Okay. Uh, that back. Okay, so if I try to make a student, Drake is bad. Drake bad with a bad name. I'm losing it, huh? Okay. Oh, was that because that is valid? Jesus, I want an invalid one. There we go. Invalid one. Okay, everything Haskell's working, guys. Haskell is still the source of truth, not your chronically fatigued professor. Okay, so we have that. How can we validate a name now? And let's make it a little bit more complicated than I did it in the slides. So let's suppose that we want a name to be two things, like and then those two things should start with the capital letter and have only lowercase letters, right? So something like this is a valid name. Right, this is not a valid name. This is also not a valid name with three things. Okay, so let's think. How can I validate the name? The things I want to do is ensure that it's two names, and those two things have capital letter and remaining lowercase letters. What ideas do we have here? All right, something totally, you could do this in a second in Python, but like how do we do it in our paradigm? What's the name of the game? What are we always trying to do in functional programming? Match patterns, right? So what's the pattern that we need to try to match here? Literally the one I just described, right? Okay, so there's an interesting function here called words. Whoops, words. And words will take any input and it will break it apart on spaces. Okay, so let's use this. So I'm going to say validate name. I'm going to make a helper function where helper validates name is equal to something. And I'm going to start by saying, let's call the helper validate function with words of the input name. Okay, so what should I test for here? Let's start easy. Let's just see if we can say, hey, is the thing that you're passing me exactly to a list of exactly two things? How can I express that? Pardon me? That is imperative thinking. And you use the length function. So now we're screwed if we are given infinite input. What did I say before this? Okay, pattern matching. So how can we detect if the input is a list of two things with a pattern match? So this is sort of yes, that is correct. Okay, so I'll do it like that. So we have X colon Y colon empty list. The thing coming in has to be a list of length 2, right? Okay, so in this case, maybe we validate as true. So I can say this is just student with this name. Oh, sorry, wrong place. We can say this is true. And otherwise, H validate name on anything else is going to be false. Okay, because anything else is going to be too small or too big. Right. So I'm literally saying this is the only pattern that I'm interested in, the one with two To list. Okay, so let's see if we get any leverage out of here. So can we validate name? Drake is bad. That should be what? True? Okay. This should be false. This should also be true. This should be false. Okay. So we've managed to pick up if these two if the thing brought to us is exactly two things, but we haven't dealt with a bunch of the other things we want to reject, right? So for example, we could have illegal characters in here, and we don't have to start names with lowercase letters. Okay. So what's the next thing that you want to address? Yes. I think that's a capital idea. Okay, so my colleague down here was asking if it'd be too verbose to define upper and lowercase letters. And I would say, well, we don't have any other options, right? You're not going to call in data.char in your exam. You're going to be prohibited from utilizing libraries. But there's this great striding, right? So we can always very quickly get things like lower. Here are the lowercase characters, and upper. Here are the uppercase characters. Okay, so I wouldn't call this very verbose. I'd say this is fairly compact. Okay, so now we have the lowercase letters and uppercase letters. How can I extend this pattern to say, okay, I want to check now the first letter of X and the first letter of Y? Because what were X and Y at this point? What's their type? String. So they themselves are also lists, right? So really, I could be doing something like this. Oh, actually, I want you to further be this pattern. You're going to give me two things, but I'm going to look at the two things. I'm going to break you two into two things. So what should X and Y be? Or sorry, what should I test X and Y for? Because we have to make this validate name a little bit more complicated now. So this is going to be what? So I validated that we have exactly two things. And what should I start checking? Okay, I want to check that. I forget. Let's look. Element. You give me an element, you give me a list, and I'll give you back a bool. Okay, so I want to check that X is an element of upper. And I want to check that Y is an element of upper. Lower. No, upper. Upper. That's the second name. Okay, so let's see what this gets us. Okay, so let's see. Can I validate this? How does it not work? This is going to return a bool, right? That's an and. Okay, so that should be true. This should be rejected. Okay, we're getting there. Okay, so what remains? Check that X's and Y's. The tails of these things are what? All lowercase letters. How can we do that? So many options from last week, right? So we'll try at least a couple of them. What do we need to do here? How would you do this with the for loop? Oh, list comprehension is a for loop effectively. Do we have list comprehension in Haskell? Which list comprehension in particular do we require? So you're going to list comprehend, you're going to get a list back of true false values. Then what? All. Okay, remember we have all. That's one of them. What does all do? It says give me a predicate, give me a list, and I'll return you bool. So this sounds like it's going to check maybe if like everything in a list, satisfies some type of predicate. I think that's exactly what we need. Okay, so what I want to do here is say something like all needs to get a function. And the thing I want to pass it is maybe we'll focus on X's. We'll validate X's. So the new question goes, what goes here? I want to check elements of, yeah, so it has to be a lambda function. So it's kind of like lambda, I'll say A goes to element A. What is this? X's? No, up lower. Okay, so let's check that. So this should be accepted. This should be rejected. Great. Okay, there's ways that we can simplify this one. So because this happens a lot where you're trying to effectively fold or do something with a function with two inputs where the input may be backwards, I'm just going to do this. I'm going to say, hey, just flip the order that we're going to give stuff to element. And then it allows me to use the point free form because like this would have been equivalent to this. And because of the point, I don't need A's on both sides. So that allows me to do that. Okay, so I suppose I just need to, okay, I want to do another one. So I think this is a really good idea. Good job. Let's practice our folding. How can we fold here to accomplish the same thing? We'll use a right fold. That's the one I prefer. So remember, folding right is like linear recursion. So what do I need to check it? If you're writing this linear recursively, what needs to be checked? Well, we have to check that the head of the list or the head of the string is a lowercase character and the remaining of the stuff is a lowercase character. So we need to check px and foo x's, right? I need to check something here. And the thing I need to check, okay, so I'm gonna fold right. I need to give it a function, so AB to something. I need to give it a base case. What base case do I fold if I'm folding effectively for all? Yep, true. And then I give it the list x's. So what do I want to do here? Well, I want to test if A is an element of lower and B. B is the recursion. Right? You can regard that as like the answer of what's happening in the rest. Hopefully that works. Yes. Okay. Let's try to construct some drakes. Change it to Y's. Thank you. Okay, so let's try to validate a name for Drake is bad. That should be true. Huh? Oh, validate name. Yes, thank you. Okay, so that should be wrong. Oh God, that's a nightmare. What else should be wrong? That should be wrong. This should be wrong. This should be wrong. Okay, so I think we can like validate a name. There would be, can we remove any of the, is there anything that we can remove from here to make it point free? Do you see any common B? B can be removed. So if B is removed, then I just got to move this and to here. Okay. And I think that's still good. I maybe have to put this here. Okay. Can we do anything else here? Can I play the same trick? Yeah, let's flip this. Yes, here I could put an A. Hopefully that still works. Yep. And then I can take out those A's and just replace this with, I believe, a composition. Okay. So I can even make that the point free form. So when you see Haskell code, note that sometimes we've started up sort of a little bit higher and the code itself has underwent a few simplifications. Like I don't really expect people to be able to produce this on their first draft. It does take a little bit of thinking. Okay, so now that we have this, I can add here, if we don't validate the name of this name, then I want to return nothing. Otherwise, we're off to the races, right? So I can actually give you just a student with this name and this ID. So let's give that a go, trying to use our smart constructor. Why did I write string? Student. Okay, so let's make a student. Drake is bad. 1, 2, 3, 4, or 1, 2, 3. Should this accept? Should this construct it? Yes, we constructed it. What about this? No, nothing. But wouldn't it be better now to actually get some information about what is going on? Like something better than nothing, right? Okay, so let's do that. Now, is there any ideas? So I got to go back to the slides to talk about either. So the ones I have in here are a little bit easier. The name validation that I have in your slides is just check that the only thing in the string are uppercase characters, lowercase characters, and spaces. think the one that we did was a little bit more sophisticated than that. Okay, so now what I want to do is sort of introduce this either data type for the purposes of now addressing this question that I just have of how can we give more descriptive feedback when encountering errors when constructing things. So I'm going to now use this either data constructor, which is effectively the union data constructor. So you can give either two abstract types, A and B, and it will construct left of over A and right over B. Right. So if you have, do I have an example? Not really. Okay. So if you do either integer string, you're going to have left of 0, left of 1, left of -1, and so on. And you're going to have right of empty string, right of A, B, C, right of all of these strings. So this is, remember, this is called a sum type because you have these ones. And this is called a product type because you have one right B for every B in the type itself. Okay. So this is going to be the mechanism by which we're going to now add types because we're going to create a custom data type for errors effectively, and then return a student or either an error. Okay, so here's an example. So here's something that where I can take sort of input that's either an integer or a string, and I can return back a string, right? So we sort of have never been able to do this, right? Sort of take something which was potentially one of two types. So I'm saying, okay, so this is why we need the left and right decorators here, right? So at the level of pattern matching, we know what is being, what's inside the container. So I can say, okay, convert into a string. So if I say match left of M here, M has to be integer because that's what's left in this either data type. And if M's an integer, then I'm just going to show it to convert it to a string. Otherwise, if it's on the right, I know that things on the right are strings, so there's nothing to do. I'm just going to sort of send it through, remove its right decorator. So now I can say convert right hello, and you get hello. Convert left of 1, you get 1. Okay, so this is sort of a new piece of technology. Here's another one, converting strings to either integers or strings. So this is now putting either in the output. I can say convert the string 1 to left of 1, right? Left, that's because where the integer is. Convert 2 to left of 2. Convert 3 to left of 3. So this is a function that converts 1, 2, 3 to their integer corresponding numbers, and then everything else to just a string, right? So I can say something like, okay, convert 1, you get left of 1 back. Convert random, you get right of random back, right? So I've now shown you how we can take a collection of types as a union, as input, and I've now shown you that we can, as output, return a collection of things. So in this case, what we want to do is just spin up a new piece of data for invalid student, perhaps. Okay, and I'm just going to put two pieces of data in there, bad name and bad ID. Okay, so now instead of returning a maybe student, I'm going to say either return an invalid student or a student. You see how this even sort of makes sense? Like literally when you're reading it, this is good. This is how we want to name things and be treating our Haskell code. Okay, so we need to change things now because now this is all the wrong type. So in the case where I'm returning where the ID was invalid, I want to return bad ID. In the case where the name was invalid, I want to return bad name. And actually what I need to be doing is saying this is left of bad name. I need to put that decorator there. And this needs to be left of bad name because we're returning an either type. And I need to specify which one of the types is it in. Is it in the left-hand side of this or the right-hand side? So, and as I said, we put errors in the left because correct is synonymous with right. So things that are right are correct. So the thing that's correct in this case is this. It is right that this student should be created. Okay, let's just deriving show here and see what we got. Okay, so now I say this and it says left bad name. Yes. I can also give it a correct name, give it a bad ID, and now we have a bad ID. Okay, but like maybe these aren't overly descriptive. So one more thing that we can do. So we don't have to derive show. I can say instance. I always forget the syntax. Yeah, show invalid student where show of bad name or bad ID is, I don't know, constructor error. Badly formed ID. Show bad name. Constructor. Error. Badly formed name. Okay. And now you see if I reload this, whoops, why is it complaining? Pardon me? Line 12. Oh, bad name. Thank you. Okay. You guys are really helpful today. That's a change. Uh, okay, what's this? This should say badly formed ID. Badly formed name. Okay, but then here's the thing now. Like, you can have bad ID zero. Can I put numbers here? Let's see. Can I put numbers in Haskell names? I think so. Yeah, bad ID 0, bad ID 1. Right? I'll say this is error code 1, error code, oh, error code 1, error code 0. Sorry, line number, please, to fix. Oh, D's need to be uppercase. Oh, thank you. And one more. 17. Oh, I should have just corrected it at the beginning. This one. That way my mistakes will propagate. Okay. Yes. 17, bad ID 0. Okay. Okay, so now if I construct this, okay, error 0. But the point is now, like, have as many of these as you damn well please for like however many situations that you want to indicate adversity against. Okay, so the sort of learning objective here is that if you want to do error signaling, we can just make it data and then pass data as pass errors as data by creating it in its first instance and then using this either type in order to pass it along, right? So we can either have functions that maybe return an answer or functions that on left return errors and right return something correct. Okay, so we'll be working with that. Conceptually, this isn't that bad. What happens now is that these decorators, all of these constructors, make coding in Haskell very messy, right? And you should be struggling with this in some of your questions on on the exorcism that involve maybes. Right, so don't worry. I will show you soon how to how we're going to handle that, how that's not going to matter. But first, we have to suffer a bit. Okay. One more thing, and that's on higher kinded types. Okay, so I've introduced two things, right? Maybe and either today, and these are kind of different. They sort of act like functions, but they return types. So our functions don't return types. Our functions return elements of types. So the question I asked at the beginning of class is, well, what is maybe and now what is either? Like we need some type of higher kinded type to describe these things, right? So that's exactly what a kind is. A kind is a collection of abstract types, and these maybes and eithers aren't function that takes types to types. These are functions that take kinds of types to kinds of types. I'll put it that way. So we have this extra now symbol asterisk, and which typically defines something like a pointer. But in our system, it's going to be a stand-in for the set of concrete types. So you know we have types like int, and we have string. Those are all actual types that are sort of like different than A or B, the abstract type. So for example, the kind of int is I'm an abstract. I'm a concrete type. That's what I get designated as. What's the kind of bool? I am a concrete type. That is to say, you don't need to give me a type in order for me to become a type. What's the kind of character? Well, I'm just a concrete type. So the syntax, this double colon, is it's typically read has the type, but in this context, you're reading it as has the kind. So here's some new data. It's for animals. And the animals are going to construct dogs given string names and cats, right, that don't get names because they don't come when you call. We've used this before. Is this a concrete type? I see some head shakes. For you shaking your head, what type do I have to give this in order for it to become a type? I don't think we have to give it a type in order for it to become. So would you like to change your answer from to concrete? Cool. It's concrete. Because again, we don't have to give this any type in order for it to become a type. It's already a type. It's a parameterized type, but it's still concrete. We know everything. What about this one? This is a data for trees which are holding abstract types in their leaves. Do I have to give this a type before tree A can become a type, a concrete type? Well, what is it then? What are at its leaves? If it's a concrete type, tell me which concrete type it is. You need to give tree a type before it can be a type. Like we can't just use this, right? If you want to put something in it, then at that point, A has to be a concrete type if you want to put something. We can't utilize something of type abstract A. We don't have a choice function here. Yeah. I'm not sure. Probably. Yeah. Yeah. That's totally consistent. Okay. Again, like this is an abstract type. So this is a type in waiting, right? Tree needs to be told what is going in my leaves. I can accommodate any type, but in order for me to actually be data, for you to actually work with me, I have to be made concrete. Okay. What about maybe? Well, I just showed you. Maybe requires a concrete type before it can become a concrete type. We can't just use maybe. We can't have a function that takes maybe to integer. You can have a function that takes maybe a to integer. And then every time that you call that function, you're going to have to call it with that a being concrete some type, some kind. What about either? What's the type of this or the kind of this? Well, maybe takes a type and gives you back a type. What does either take? Two types and returns a type. So what do you suppose the signature will look here? Three asterisks. Give me a type, give me another type, and I'll give you back a concrete type, right? The concrete type of either over two things, right? So remember, we're always partially evaluating. So if I give maybe, oh, sorry, well, belay that last thing I said. What is the kind of maybe int? Do I need to give this any more information for it to be a concrete type? No, maybe int is a concrete type. Now reload the last sentence. Remember, we're always partially evaluating. So if I give either int, what is its kind? I need still one more type from you before I can give you back a concrete type. What's the kind of either int? Concrete. Nothing else is required in order for me to work. Yes, sir. As a Haskell? Yeah. Second argument. That's the point, though. We've partially evaluated either, which is what we're always, don't forget about currying it. We're not actually ever giving two things to a function. We're always doing the one and then the other. So just to prove it to you, wouldn't this be funny if this errored? Thank Christ. Okay. Throw away the whole lecture. Okay. Determine the kind signatures for the following type constructors or indicate that an error will occur, right? Because if I give maybe, Haskell's not going to like that, okay? Because you have to give maybe a concrete type, and maybe is not a concrete type. So with that spirit, is this going to work? Can I give maybe int? Is maybe int a concrete type? Then yeah, that's totally fine. Is nothing in this? Yes, the top level nothing. We also have just nothing in this, so there's the two nothings. So we would never use a type like that. That would be kind of crazy. What about this? What's the kind of either maybe int or maybe string? Concrete? Is this concrete? Is this concrete? Either's getting two concrete types, so it is concrete. What about either, but I give it either int string? Still, I need one more concrete type before I can become a concrete type, but thank you, sir, for the first one, right? Because partial evaluations is fine. Kind maybe, bomb explodes, right? Error, right? Okay, cool. Are we almost done? Okay, so determine the kind signatures for the following type constructors or indicate that an error will occur. What's this? So what are we looking at here? Am I asking for the kind of empty list? That's the list constructor. I can construct lists. Oh, I should have been able to. Maybe I shouldn't be trying to do this Well, in any case, you can still ask for the kind of this. There is a way to call it. I just kind of forget. I think maybe I have to call cons. But yeah, but don't interpret empty list in this context um as the empty list. The reason because of this is because it's the stupid sugaring. Like there's a lot of syntactic sugar in Haskell where if you're typing as a list, it's going to interpret it just one way or another. I'm not the biggest fan of syntactic sugar for that reason, but once we get the binding sugar, we'll appreciate it. But any case, this is saying you're the list constructor. You need to give me a type so you can become a type, right? Like we can have abstract list types as sort of in function headers, but by the time the function's actually getting invoked, by that time it knows it needs concrete types. Functions can only operate on concrete types, and higher kinds can operate on types themselves. Kind, give the list constructor integer. And now it's concrete, right? It's the concrete list type of ints. What about kind of int? Well, it's the same thing. It's weird that it would not apply to sugar in one case, but in another. But lazy evaluation get kind of weird. Um, can I give maybe the list constructor? Is this going to work? No, it's like the same thing as giving maybe. What about the kind of maybe if I give it this list of int? Concrete, because list of int is concrete. Okay, so here's a bunch of other exercises that you can do. Given the ID function, what is the kind of a? Right, write a factorial function that returns nothing if its input is negative. That may be harder than you think because you can't tie your recursion. Right, you want to say n times factorial of n minus 1, but you're going to say n times jest. There'll be a jest over it, right? So you have to sort of remove them and put them back. Given R, this type of constructor, what are the kinds of A and F of A? We'll have a better understanding of this. That sort of means a functor. Right, a functor is jest that tests for the presence of a jest in some maybe type. And what is the kind? What is the kind of function application? Because function application is also a type constructor, right? We can construct functions themselves. So guess what this is before checking it with your REPL, because you can check with your REPL. Okay, no break today. No rest for the wicked. Okay. Um, so now we're going to talk about testing, which isn't very glamorous. I'm going to go very quickly over the unit testing because I imagine you all know what unit testing is. That is when you have a function and you just sort of like give it a bunch of input output expectations and you try to do that in such a way where you get a bunch of coverage. Now, the one I'm mostly interested in is this property testing, which is a totally different mode and something that Haskell, well, in the functional programming paradigm, sort of pioneered. So it's fairly interesting. I'll just check in on the chat. Chat, you still doing okay? Everything you can hear me? I mainly just do this to see that they just didn't log in and go watch Netflix or something like that. Big thumbs up. Okay, cool. Okay, testing. It's not sexy. We have to do it. Okay, it's important that we test our code. So broadly speaking, our testing in this course is going to fall into two categories: unit testing and property testing. I'm not going to test you on unit testing. I think there's usually like one or two. There's certainly property testing on your assessment, and there's usually like a slow ball property testing question on your exam. So just keep that in mind. So in unit testing, we assert a function's output for finitely many inputs, which are chosen by us, striving to include edge cases in typical cases, right? This is sort of an art. I really can't give you a systematic set of rules to follow to get total coverage in your tests. But for this, we use HSpec. And indeed, this is what we're testing your code, your homework code, using this HSpec library. But more fun, there's this arbitrary type of testing called Quickcheck, which is going to be the second half of this lecture. So let's just focus on like the easy part of the lecture. I have a function foo, it takes two ints and returns an int, and it's just going to multiply those integers together. So I can basically assert that foo given 0 and 0 is 0, and foo given 2 and 3 is 6, right? So those are both what we call, I don't know if those are individually unit tests or comprehensively, it's a unit test for foo. But what we're doing is just designating input output expectations through assertions. Now, in order to get access to these testing apparatus, you would have to install the entire tool stack for Haskell. We're not engaging with actual like Haskell software toolchain creation. It'd be a huge distraction. So you can either install the entire stack if you want, or you could install just the HSpec and Quickcheck libraries through these Cabal. So Cabal is like the Haskell installer. So this should still work. I haven't tried one of the years. If it's broken, tell me, and then I'll update the slides. But last time it still works. Fantastic. Okay. So do this and it should work. I have one, my colleague over there says this is working. Okay, so this is going to install HSpec in Quickcheck for you. It's you don't have to actually do this because we're not going to give you any assessment pieces where you're going to have to write quick checks like that actually run in the system. This is only if you actually want to play with it. So I guess if you don't want to install this, you don't have to. So here's how the HSpec package works. So suppose we have the following sort of trivial functions. One that just adds two numbers together, that's foo. Another one that multiplies, that's bar. How could we write some unit tests for this? So in the same directory as this sandbox file or module, the word module and file are kind of synonymous in Haskell. What you want to do is create this sandbox spec file. Now, sandbox spec is just the naming convention. You don't have to name it sandbox spec, but it's typical to name the testing file, the name of the file that you want to test, spec.hs. So we're going to just lean into that naming convention. And you have to define this main routine, which is a sequence of IO actions. And we're going to build this soon. I just can't tell you very much how it works. But for now, we can just understand that these IOs, monads are effective. They're going to briefly let us sequence actions and print things, right? Which is a seemingly total violation of our functional purity, but it won't be. Right? Again, remember, week 12, print hello world, rousing applause. Right? That's what's going to happen. Okay, so for now, just follow the framework of this. Don't worry too much about the syntax being sort of indiscernible to us. It will be. But basically, I just want to say, okay, run HSpec, this function. And what do I want HSpec to do? Well, I want it to run this description of the function foo, where this is doing some tests. And this is the first iteration of the test. This is the second iteration, right? So this is kind of like a while loop, but not really. So do this iteration. This is a description for the test, and do check that foo11 spits out 2, that this should be the same. This is sort of like an assertion. It should be the case that foo, when given 1 of 0 is 0. And then you want to give a different description for every other function in the sort of same way, right? I want to do some type of iteration on my test. This is the test description. This is sort of what's going to get output if you fail. We know here that bar 1 times 1 should be 1. Again, not too sexy. Okay, so here's what's in my directory, the sandbox module and the sandbox spec. You can say run Haskell on this. This was always available to us. If you run Haskell on a file, that will just run whatever's main, right? It looks for any, we're not actually allowed to define a main function. This is sort of like the if name equals main part of a Python. It's like the entry point for Haskell calling into this file. So this is going to call the main routine, which is the thing that sort of sequenced all of our tests. So this is what you're going to see. You're going to see foo. You're going to see the test description that you put in there. And you're going to see the test description. And you're not going to see anything effectively. If you don't see anything, that's good. This is effectively saying that you've passed all the tests. If you failed them, it would specify which one you failed, and you'd go and correct it. Okay. So this should work. So you should be able to import test.hspec. And you get this should be function, which is kind of weird, right? You give me 2 values and I return to you back an expectation. What is an expectation? It's a system level thing. Okay, so I know this is very unsatisfying when it just says, I'm kernel, go away, right? You don't need to know anything about me. Don't look at the man behind the curtain. I'm C code. You're not going to understand me anyways, but that's what it is. So don't worry too much about this. I don't really care about HSpec, but you will use it if you want to go to use functional programming in industry. And Jesus, they keep calling me. So when I first started teaching this course, I'm like, I don't know, it's a bit of fun. I doubt this is going to be overly useful for most people. But it doesn't seem that the chat GPTs can do functional programming, right? So all of these functional programming companies are like trying to take me out for dinner and stuff to get access to you guys. So become good at this, and I think you're going to be able to insulate yourself against some of the, I don't know, these pieces of tech, like imperative programming. I don't know how many jobs will be left, but functional programming, they're trying to find me to find you. So if you can get good at it, I think there are jobs, but it's higher order reasoning, which is good. It's good. This is where you want to train into, where the chat GPTs can't find you yet. Have you been doing the Ghiblis and the Disneys and no? I did a Barbie one the other day. Don't do it. Oh my Lord, that was just nightmare fuel. To see myself as an actual Barbie, it's terrifying. Okay, this is what I care about. Okay, I don't care about, well, I care about unit testing the same way that you care about it. We hate doing it. We know that it's a necessary evil. We're happy when it catches tests, when we break tests that before we have to submit something. But this is genuinely interesting and something that you will be tested by. So instead of like I want to check properties of my functions rather than like simple input output assertions. So we want some way of checking formal properties of our programs very fast. So then let's walk through sort of how this technology was created. So again, we're not going to be testing units. That is to say, f of x should be y. We're going to be testing some property that we suppose f should have. So here is an example of a property test. So what should be true about the function reverse on arbitrary list x's and y's? This isn't a test on a single unit. This is a test about the very nature of reverse itself. Does this make sense to you? If I concatenate two lists and reverse it, that should be equal to reversing the second list and concatenating it to reversing the first list. If reverse was implemented correctly for any lists x and y's, this has to return true. Agree? So would you agree that this is a property that the function reverse has? Okay, so here are some other common properties where we usually want to check that, like if we're adding 0, it acts like 0. If we're multiplying by a unit, it acts like multiplying by a unit. If we multiply by zeros, that should produce a 0. Maybe those ones are obvious. The 3 and 4 are maybe less obvious. Have you heard this term idempotency and involution? So to be idempotent means that if you call the function once, if you call it again, nothing changes. Can anyone give me an example of an idempotent function? Okay, non-trivial, but you know what? Best answer. If this was a test and I said something as foolish as that without clarifying that you should give me a non-trivial example, give me the trivial example. It'll be if you give me a technically correct answer on your exam, full marks. And sometimes I'm even like, you rascal, full marks. Like a few years ago, I asked for like the 100 Pythagorean triplets. I think that was one of your exorcism questions. Someone just wrote 3, 4, 5 and like put that in a list 100 times. I'm like, heck, yeah, technically right. You get this, right? So when I'm writing these exams, it's so hard. I got it. Like the reason there's so many words in your exams, the reason we can't give you a simple exam is because some of you should be lawyers and not mathematicians, right? I'm 100 times more stressed when you guys write the exam than when I used to sit exams. I just sit by my phone and wait for the proctors to call me and say that there's emergency, which happens 100% of the time. We'll talk more about the exam. Okay. Non-trivial idempotent function, please. If I negate something twice, it's the same as negating it once. Why don't you save your answer for involution? Okay. Yes. Yes, sir. Sorting a list. Sort a list. Okay. Sort it again. Nothing changes. So therefore, sort has the property of idempotence. Can we think of anything else that has an idempotent property? I actually can't think of one. Oh, constant functions. Yeah, that's another one. Maybe a function that empties a list. Yeah. Oh, that is also a constant function, I guess. Yeah. Absolute value. That's another good one. Okay. So that's what idempotence is. If you apply the function once, it's the same as applying it twice. And some functions have this property. Involution is another fun one. If you apply it twice, you get the identity function. Would you like to try again? Negation, right? You apply negation twice, it cancels itself, right? So that's negation has the property of involution, right? So idempotence, involution, you should keep those in your pocket. Those are some sort of good properties because this one you really do have to think. Now, the reason this was provisioned is because next week when we do functors and applicatives, the functors and applicatives that we introduce have to satisfy a set of properties. And when we define them in Haskell and then use Quickcheck to quickly check that those properties hold. Right. So that was the true reason that this got input into the system, but it's actually more widely applicable now. Okay, so if we wanted to sort of take this reverse example and sort of shoehorn it into HSpec, we could do that. So here's like the sort of unit test where I'm saying, okay, it should be the case that reverses of x's attached to y's is the same thing as reverses of y's plus reverses of x's, where, X's is that list and Y's is this list. I just chose them arbitrarily. How many of these X's and Y's should I choose to check this property? Yeah, ideally infinite. Practically speaking, more than one, right? And hopefully things with like edge cases and stuff like that. So the answer is probably the more the better. Like if it's not sort of computationally troubling to run them. Should I just go here and then just start writing a bunch of these unit tests, like 1,000 of these to check this property? Answer is no. So it seems that our selection of input here was arbitrary. I don't care what goes in X's and Y's, really. So we have so what Quickcheck gives you access to is this incredible function, which is a sort of like a function constructor where you can get arbitrary things. Okay, so when you call a Quickcheck like this, so I'm saying Quickcheck and take X's and Y's to this property. So Quickcheck, give me two lists and check this property. And what Quickcheck is going to do is choose at least 100 different list combinations, choosing wisely, definitely choosing like empty list, not empty list, both empty lists, non-empty list, empty list. Like it hits all of the edge cases and then does 100 more. And we can tell it to do 10,000 if we wanted, but it's going to do at least 100. So the relevant thing is here, when you call Quickcheck and you give it a function, it knows how to work out using type inference, how to give the input arbitrary values, and it will run it. So this gives you 100, one line in Haskell gives you 100 unit tests. So this is why you want to do quick checks and not these. Like you can generate these like really quickly, right? Just in one line. You sort of have to be a little bit more clever than writing unit tests. Okay, so let's try writing some quick checks now. So quick check provides access to this arbitrary type class. Because we're not using the tool stack, we have to hack Quickcheck into the system. I've been assured that these instructions do still work. So do the following if you get errors about test.quickcheck failing to load. This command or this one. One of them should load it into the system, right? Because you basically want to say load, like run Haskell, but make sure you have access to Quickcheck, and one of these two should do it for you. I'm not sure why. It seems sort of semi-random, right? Which one of these are going to work, but one of them should. Otherwise, ask on the EDSTEM. Okay, so I'm going to go into Haskell, loading the Quickcheck library. We're in. I'm now going to import the Quickcheck library. And I'm going to say, okay, can you please Quickcheck for me the commutativity of the identity operator of multiplication? I'm saying Quickcheck the fact that x times 1 is the same thing as 1 times x. And Quickcheck realizes that, oh, okay, these are going to be what type? What's the type of x? It's a number, okay? So Quickcheck is going to say I have to choose 100 arbitrary numbers to run this. And some of them, I should choose 0, I should choose 1, and a bunch of other stuff. And this is going to say, no problemo. You passed the 100. Okay, what about this one? Check associativity of addition. Check that x plus y bracketed plus z is the same thing as x plus y plus z. Is this true? Okay, so this should pass quick checking. Okay, so it tried 100 times. So far, maybe this is just fooling us. Okay, let's try and verify that exponentiation has the associativity property. Does it have the associativity property? Should this then fail? Okay. Okay, give me an example where it fails. 2 to the 3 to the 4. Oh, yeah, I guess. So the fun one is just irritating the mathematicians with the 0, 0, 0 example. If one of you send me an EdSTEM announcement about the limit of x goes to 0 of x, I know, right? This was an arbitrary decision that was made. But what is 0 to the 0 in Haskell? 1. So if this is 1, what's 1 to the power of 0? 1. Okay, but this one is going to be 0 to the power of 1, right? So that's 0. So 0 isn't equal to 1, last I checked, hopefully, even though, ChatGPT told me otherwise yesterday, so I'm unsure. But we expect this to fail, and here we go. Not only did it fail, it said here's a case where it fails. It doesn't work on 0, 0, 0. Here's your counter example for your assertion. Right? And it probably 0, 0, 0 was like the first thing that it checked, right? I can't really verify that, but I would guess that it starts with edge cases and then goes arbitrary. Oh, it's probably the first test that yeah, cool. Okay.
I suppose I can't make the assertion that that will always be the case, but in this case, it did. Okay, so here's the quick check for reverse that I gave you in the first slide. It's called the distributive property, right? You can distribute this reverse across this operation, but you sort of have to do that swap afterward. Any other ones? I always get silent. You have to sort of be creative here. Pardon me? A times B. I'm saying for reverse. Can you give me any more properties for reverse? That, yeah. You both can have points to your respective Hogwarts houses. Hogwarts, it's Ravenclaw. Slytherin. You give us Slytherin vibes. Yes. What did we call that? That was involution or involution. Reversing twice brings no. Yeah, involution. Reverse dot reverses the identity function. That's a good one. Any other ones? You got to get kind of creative. Okay, so you reverse the list. What happens to the head of that list? Becomes the tail of the other list. So that's a property check. You're saying, look, if your reverse is working, the head of your list should become the tail of the reverse of the list. And the opposite of that is true. If you're reversing this list, your last element needs to be the head of the list reversal. That is a quick check. That is something that has to be true if reverse was implemented properly. Let's see what other ones I had. So involution, that's the one you guys got. Oh, the maximum of the reverse of the function has to be the maximum of the list, right? No new elements can be introduced in this operation, right? So these properties, yeah, like they don't like this is a fairly significant property for reverse. This is sort of a weaker property, but they're all properties that these things have to hold. If somehow you introduced a new value, right? Suppose you multiplied something by like a negative and suddenly now you have new minimums. Like that would trigger. Okay, so that passed. What's this one? Is this a quick check? I guess I'll say technically it is a quick check, but is it a property test? What property is this checking? So this effectively is just 100 unit tests. Okay, so here's the problem. So I need to be able to say something like, give me a useful quick check, by which I mean example 1, example 2, example 3, and don't give me 4, which is just a way of encoding 100 unit tests. Okay? So there's not really any better way I can say it than that. Give me something useful, right? You won't get marks for this on your exam or your homework. We'll say this just encodes a bunch of unit tests. It's not really a property. Okay? So that will work, and it technically goes through quick check, but I don't think it's very useful. It's like, so really you're safe. The reason that this sort of doesn't get marks is because you're not letting the list be arbitrary. You're like picking arbitrary elements and putting them into the list. So normally you're safe if the thing that you're testing is properly the thing that's been made arbitrary by quick check. Okay? What property must the output of smallest satisfy? Here's an implementation of smallest using a fold. So I want to find the smallest integer in a list of ints. The reason I chose int is so we could use max bound, which is going to be plus infinity is going to be what the smallest element of the empty list is going to be. If that puzzles you, go back to the lecture we did on sort of working out weird base cases. But what are some quick checks that we can, like, suppose you don't believe me that this works. What are some properties of smallest that we can implement? It's like anything that has to be true. The smallest, okay, so we have a property here that whatever smallest x is equal to has to be smaller than or equal to every member of the list. I think that was, yeah, smallest x's must be less than or equal to every member of x's. That's a great property check. There's other ones that we could do here. Sort the list. Its head has to be the smallest element of the list if you've done it properly. Any other ones that you can think for smallest? Yes, sir?
You,
Just like, fine.
oh, so you're saying that quick check effectively tests, like basically is a proof that the thing is working?
Yeah, like theoretically.
Well, but we can't check them all. Like in order to get to validate the program in all cases, we'd have to give a mathematical proof. The way Quickcheck acts in, so I'm saying we're going to use Quickcheck to sort of certify that the functors and applicatives we wrote work. But really, Quickcheck just basically says, hey, probably the thing that you do is working. Probably. I mean, we couldn't find a counter example, but it's like there is no number of tests that we can make which prove something is working unless we like really go over the entire domain. Like I suppose we could do it with integers by checking literally every integer goes to the thing that it's supposed to. But anyways, what else do we got? Okay, so here's how we can quick check exactly your suggestion. So I'm saying, okay, quick check. Take x's, so give me an arbitrary list, and it should be the case that the smallest member of this list is smaller than everything in the list. Okay. Well, here's another one. The smallest of the concatenation of two lists should be the minimum of the smallest of x's and smallest of y's. This is sort of like a distributive property, so that will also work. The smallest of what about this? Oh, so this is just another way. This is interesting because you're using smallest in its own property test, which is fine. If smallest is working, the smallest of x's concatenated with y's should be the smallest of when you connect smallest of x with smallest of y's. That's going to be a list, which you can then give to smallest. And if it's working, this should be working. Under test passed. What properties must sort satisfy? And ascending. So we're going from the last thing should be the biggest. I guess that's in itself a property, right? So I'm saying we're sorting, we're ascending. There has to be the property that if you sort x's, that its last element has to be the biggest. Yes, sir. Every element is smaller than the last element, smaller than or equal to, yeah. I guess. Oh, yes. If we sort, then sort obligates that the type has to be from the ordered class. Yeah. What else do we have? Do we have that was idempotence? Idempotency is at play here. Sorting twice doesn't change anything. Okay, so idempotence, sort of the sort, gives you the sort. What about this one? Oh, there's just a missing pause. This one is, I'm saying that the head of the sorted list is smaller than everything in the list, which is sort of like your version, but from the other side, which is great. Now, so here's a problem though. How do we avoid the empty list in some of these comparisons? So what I'm saying, like when I said if we sort the list, that every list member has to be larger than the last one, that sort of implies that there are members in the list. So how do we avoid the empty list? What's this one? Oh, sorry. There should be, oh no, here's avoiding the empty list. So I just sort of glazed over it. Right, because in this one, the thing that I want to check is that what am I checking? That this is the secret sauce, right? So I want to tell Quickcheck, hey, avoid using the empty list. So I can either work that into my test, as my colleague up there suggested, say, oh, you're not the empty list, and also this condition is true. That would work, but that's kind of messy. I don't want to build that into my property. What I can do is tell Quickcheck, I'm saying, hey, give me a scalar and a list, and then check that. Right? This is basically saying, hey, like you own, like the smallest list that you get to play with is one with at least one element. Right? So you can always ask for a bunch of scalars. So if you wanted at least list of length 2, you ask for x and y and the list. Right? So here's just a funky way of avoiding empty lists, which you'll have to utilize on your homework because I'm asking you to write some quick checks for your variance tail function. Okay. So here, write some quick checks for the following functions: a function that like caps something, a function that's sort bigger x's. I don't know what that one means. I'll have to fix that one. So there's quotient and remainder, and they have a property, a mixed property. Like, right, effectively some statement about if you divide y by x, it's like the quotient times its divisor plus the remainder or something like that. So you should be able to codify that into a quick check that's actually testing both.
Try to get a quick check to tell you if fold R and fold L are equal functions. And if they're not, it should be able to uncover, well, are fold R and fold R and fold left equal? I think there's a lot of things that depend when you say that statement, like the operator that you're folding with has to be commutative. I think would be one of the requirements. So you should be able to use Quickcheck to get a counterexample for this. And for this one as well, you're sort of a function. F takes n and x's, and it gives you back the length. Oh, so take n from x's. I want the length of that, and that should be equal to n. So find out if this is true using Quickcheck or not, and it should give you a counterexample if not. Okay, so next week, it's going to be, you better bring coffee, because we're going to start doing some pretty significant theory next week. So it's going to be like functors, applicatives, and then state changes, monads, and then IO. Okay, so a lot of theory and proving, and then parsing, which is going to be fun. And then an industry speaker is coming in, because the EdSTEM decided that rather than me giving you the review lecture, that you want an industry speaker. So I got industry coming in. You can always watch the review lecture from the year before. Okay, I just want a little bit more of your time. I will let you go a little bit early today because I have been robbing you of breaks this whole time. I just want to do like a little mid-year checkup because I like stripped a bunch of exam questions. Are we getting questions from the chat next week after the mids? Oh yes, we get an Easter break, everyone. So enjoy your Easter. Okay, so I just want to do like a little checkup because I stripped from the exams a bunch of questions that we should be able to do at this point. And they're like the quick ones. So I want to just ensure that we'd be able to do them. But also I want to talk to everyone because something weird happened last year and I really don't want it to happen again. So this is mostly like a conversation for people here who have joined us through partnership universities, but generally, I know this is true for everyone. Okay. So this is how exams work at this university. I prepare two exams, exam A, the primary one, and exam B, the deferred one, right? So if you can't make it to the first exam, or if you get sick or something, you get a deferral. Or if you fail to get an adequate grade on exam A, you may be eligible to take exam B, right? That's called the supplementary exam. So is everyone familiar with this notion of being able? Okay, great. Okay. At this university, every student is given one discretionary deferral, right? That is to say, you can defer your exam for no reason once. And if you're from a partnership university, it's very tempting to use this because you may not ever be back here again. So you're just thinking, I'll get some more time to study for the exam. Here's why you shouldn't do that. The course is ended by the time the supplementary examination is running. So a lot of these students who've taken this discretionary token then get really surprised when they ask questions on the EdSTEM and there are no tutors because my tutors no longer work for me, right? Their contracts have ended. The term has ended. Okay, so if one of the things that are a downside is you're going to get much less support than you would otherwise get if you're taking the actual exam. If you've deferred your exam to the deferral and then fail, then you're going to have to, if you failed exam A, then you're allowed to take exam B, which is fine. Exam B is written. It's still done during the exam period. But if you've deferred, take exam B and then fail exam B and require a resit, you have to write exam C. There are 300 people in this class. 100 students last year deferred to exam B, 100. I was furious. I had to mark those exams. I didn't have tutor support anymore. This was a total exploitation of the deferred system. Okay, so so exam B becomes our lowest. So you now need to write exam C. You've flown back to the country that you are visiting from. You say, oh, professor, I failed my exam B. I need exam C. And then I don't get back to you for a few weeks because I need a rest intersemester. Okay, so after I take my couple of weeks rest, I come back and I say, you may take exam C. You have to come back to campus to take it. We don't do external testing anymore. The whole apparatus it's not trustworthy. That's why we can't do it. Too many of the centers were infiltrated. Okay, so you have to come back. Furthermore, these partnership universities then start emailing me furious saying, we need to designate the student with the grade. And I'll say, okay, fail then. Right now, fail, or wait, maybe not fail, up to the student. Okay, so partnership universities get tilted, and there is zero support for taking. I'm already teaching term 2. I can't give you any attention if you're taking exams. I'm already angry that I even had to write a 3rd exam, and then I comprehensively have to mark that, and I am tilted. Okay, so like 1/3 of this class deferring to exam B was an unacceptable amount of deferrals. So please don't do it. It created a lot of problems. And then I don't want to hear this. I don't want anyone coming to my office and asking me this question, not at the 3rd year. This is an unacceptable question to ask me as seniors. Do you know what the answer to this question is? Do 1 week of this course every day for, like, I've given you the course pathway. That's what we're currently doing. I'm not withholding from you the 5-minute way of onboarding Haskell programming. If you want help, come get help now. That's why I'm telling you this. I'm so willing to help everyone accomplish this course to the degree that they want to accomplish, but the help has to happen now. The help cannot happen after you wrote the exam. Too late for help, right? Come to me for help now, and please don't use those discretionary deferrals. It's not worth it. Most of those students who did that didn't utilize that time for studying. And then the final thing is I'm known to sort of give a lot of exam hints throughout the year. I'm sure I'll start like as soon as I write it, I'll start blowing it. Like you better be able to use a single list comprehension to generate integers. There we go. There's one already. Okay. If you decide to take exam B, I got a lot of emails back. Oh, hey, are all the hints that you gave on A relevant for B? It's like, no, those are relevant for A, not for B, right? So you're also going to throw away all of the hints that I'm giving you. Now, if you genuinely, if you have like a real reason for taking the deferred, I will support you. I'm not going to throw someone under the bus who broke their leg or something like that. But I do have a way of checking who's deferred for what reason. And if it's discretionary, then I'm going to have some discretionary decision making about not providing you help. Okay. Speaking of the exam, these are all questions taken from the first part of the exam. So the exam format is the same every year. There's 10 sort of like short, like very short answer, like sort of 1 number, 1 line type of answers, followed by short answer, followed by 1 long answer. And the long answer is like usually a proof or something like that. So you will have to do Haskell programming on your examination. So be prepared for that. So can anyone answer this question? So yes, without the trolley way of doing it. Well, it is a list comprehension, but you have to be, what are your strides? So the problem with this question, so you cannot give me divergent answers. So can you give this to me in such a way where it actually will terminate? So one of the obvious, okay, so maybe the obvious way here was to do sort of something like this. I want, okay, so I want X, Y, Z such that, oh, sorry, wrong language. X is drawn from something, Y is drawn from something, and Z is drawn from something. And then, is this right syntax, everyone? It's tough. And then I just write a condition, yeah? And the condition is X squared minus Y, plus Y squared minus, oh, it's equal to Z squared, yeah? Is it? It's the wrong language again. Okay. But what goes in there? Okay, so like, is this what you're sort of saying? So will this work? No, this will run forever because it's going to ask, remember, these are like for loops. So it's saying for X from 1 to infinity, for Y from 1 to infinity, for Z from 1 to infinity. That innermost for loop will never terminate. Yeah. The length of which list? The outside list? And communicate that inside the comprehension somehow? Huh? No, but there's not one element that will be generated in this list. If I take 100 from this, like it's just going to think forever. And there is a way to answer this so that it doesn't have to think forever. How do I fix this? Is that the correct way of doing it? I think you've done it. I think maybe we got to do this because it's for loops, and this is the outmost for loop. So I think this will maybe work. Yes, and why? You're right. Yeah, no, because I have to take over it because they're an infinite. It's searching for maybe take one. I think I have to reverse this. This should be Z. Z goes for forever. And then Y can run to Z and X can run to Z. But seem trickier than we may have thought. Okay, yeah, I have to reverse it. Okay. But absent of these interior ones having finite, like having endpoints, it would have been wrong. So you got to be careful with these list comprehensions, right? Because I'll specify that if you give me divergent answers when a convergent one exists, you'll get it wrong, right? Because this wasn't right. It just wasn't right. Yeah, not even right theoretically. Okay, so that's the answer for that. So I'm just like trying to tell you how I was trying to trick people on these examples. I'm making it very obvious, right? So don't get tricked by the same way. What's the answer to this, right? We just had a bunch of practice. So I give you a function that takes a to a to a, and I give you a, and I want a back. How can I get this? So we'll just move it over here. Let's just go. Okay, so we want something like that. How can we get something like that? Well, let's think. So I wanted to find something f, and the way I usually do this is I say, okay, I have a function which takes a and a to a, and I also have a. So how can I get a back? Okay, so I'm gonna give. Okay, so let's look at this. Okay, so who can we predict the type of f? What is the type of f? Certainly, what's coming out is going to be a, right? That has to come out of this function. So I think we're going to be fine here and here. But let's take a look. Does that seem right? No, right? Because so we're passing in a and a. So this is guaranteed to be a, that's guaranteed to be a, but there's no constraint on what's coming out. I need to somehow force that to be an a as well. How do I force that to be an a? Yeah. Sure, if you think it's going to change the type construction, I'll get out of work. Array, I'm lost. Sorry.
With like the return
List with the return value. Okay. Oh, but we already know that the output is going to. Okay, I'll show you that maybe if I give this as input to itself, that will fix the problem. Right? Because now the thing coming out of this has to be the same thing going in. Whoops. Do I have a... Oh, colon F, yeah. Ah, Jesus, Murphy. Okay. So that was the trick there. You just had to sort of make like one of these recursive calls. I think maybe what you were saying could be... Yeah, I think probably we could do it your way. Like put a bunch of stuff into a list and say that list was like the output type. I'd have to think a bit, but I think this is the fastest way of getting her done. But I think that probably would have worked. Okay, so there's your answer. I don't know why I gave that one was sort of unnecessary. I just said, okay, we'll put them out, put them back in. Define a function f with this type. That's boring. Let's do something else. For what? Well, you can do it at home. I want to give you back 10 minutes that I owe you. For what value of x's does fold right fbx's equal fold left fbx's? What is fold right if I give it empty list? What are the inputs to fold? What is B? The base case. When is the base case thrown? When you give it the empty list. Okay, so when is this expression equal to the expression on the right? When X is his empty list. If X is his empty list, this folds to what? B, its base case. If the X is his empty list, what does the fold left evaluate to? B, it's empty, it's base case. So the answer to this question is X gets empty list. And they're not tricks. The original, like the first 10 questions, I'm not really trying to trick you. Okay, so here's an example of a question I did ask on a test, right? Here's reverse. Let reverse be a function, reverse is a list, and write a useful quick check for reverse. I just want to show you this question so you know how I'm asking it. And I'm going to say, look, just write, like, use X's and just assume X's has this arbitrary type, right? So I just want you to answer something like this, right? So I'm just going to specify, like, write me a quick check for this function. Assume X's and Y's are arbitrary types. Just utilize them as arbitrary types and write me some type of quick check. Your quick check does not have to run. You don't have to write quick check on your exam. I just care about the property. I don't care that you know how to encode it or not. Okay, so this is sort of what this is a perfect answer for that question. So please don't be confused by this. So you don't have to write a quick check that actually runs in Haskell. And I just want you to utilize sort of the inputs and treat them as arbitrary, like as if the whole thing is wrapped in a quick check and you have X and Y's with the arrow. Okay. What's the type of this function? Be sure to include any class constraints. Well, like, what are things that you're seeing here that should be setting off alarm bells? Yes, miss? Yeah, the first thing that hits me in the face is that we're doing a comparison. So we better have the case that X and whatever the inside of this list are for one, the same thing, and the same thing from a type which supplies ordering. So what else is this? What does this function do? Yeah, well, returns the second input if this is bigger than the head of the list. Otherwise, it just returns the singleton list. So what do we suppose it's? Okay, so let's try to guess at its type. So I say foo takes a, foo has to take something that is from an ordered type A, and then it takes A to list of A to list of A. I hope I'm right. Aha, we were right. So that's how you have to reason through these things, right? So take some thinking, but I don't think there's like really sort of a lot of confusion that you have to unwrap. What's the beta normal form of this function? Using Haskell ordering. Okay, do you see any, is there any reducible expressions in here? Is there? Which one? Well, I see one abstraction, so that means I have to go inside. You're telling me there's a reducible expression here? Haskell ordering. So if we see three expressions, A, B, and C, what goes into what? So here's A, there's B, and there's C. And we put what into what? B into A. Can we put B into A? No, we're in the abstraction. Ignore this. Can we put this into X? No. Is this a reducible expression? No. What is the beta normal form of this expression? This expression. Okay? I wouldn't say that, like, but that's important, right? Like what the terminating condition is on these things. Right? So you understand this isn't a lambda expression. This is just like a number like 2. You can't evaluate that at anything, right? So and so the problem is you could put this into here if we weren't insisting on Haskell ordering. But we do insist on Haskell ordering. Why do you suppose that? Because we're working with a Haskell system, so we might as well stick to the evaluation strategy of the programming language that we're using. But keep that in mind, right? This one was maybe kind of a trick, but not for those in the know, I suppose. Oh, you won't know this. We haven't done functors yet, so let's skip this. That one's good to do at home. No, Okay, so here's some examples of like the longer questions now. So this one I asked in 2023. So I'm going to give you an integer and a list of integers. And I want you to tell me the number of ways that you can make the target with like summing in there. So like I usually give something that's like very evidently recursive. And this is one of the things which are going to be very evidently recursive. So give this one a try at home if you want. Oh, and there's the answer if you like. And what you should be collecting already are like functions that you use all the time on your cheat sheet. You should be preparing your cheat sheet sort of as you do the year. I'm not going to ask you any memory question. I'm not going to give you some exotic Haskell function that you've never seen before, but certainly stuff like flip and anything that we've covered in like lecture slides or in your homework, that's kind of fair game. Okay, so from this point on, we're going to be upping our game in terms of introducing higher order patterns. The remainder of this course is effectively going to be cleaning up the mess that we just introduced today with lifting kinds and signals and stuff like that, right? We can recover error handling by decorating stuff, but decorating is going to make it a lot harder to write code. So from now, we're going to fix that from now on. So you guys have a good Easter break. We will be offering EdSTEM support like as usual over that reading week. So do ask questions. Please do at least open A2 and read it, load it into your mind. Otherwise, go eat some chocolate, rest up. I'll see you guys in a week. Oh, 2 weeks, after Easter. Yeah.